Good morning, everyone. I sent some videos yesterday morning. Did anybody pay attention to those? I'm going to take that as a no. So please review those. We are going to use those things today. I was hoping that somebody, at least some of you, would look at the videos. They're sort of the best review possible of concepts of gradient and divergence that, to my knowledge, exist online. So have you all used Khan Academy ever? For what? SAT prep. Anything else other than SAT prep? So I have found their reviews really good, especially for calculus. For multivariate calculus, and I'm actually doing a little bit of it. I'm going to run one of the examples in class. But today, the best visualization that I have found for multivariate functions in their derivatives and various operators. So you need multiple derivatives, and you get a gradient. You can look at the gradient of a scalar function as well as a vector function. We will kind of need all of those. And there are two people, Sal Khan and Grant Sanderson. I have luckily written notes. I keep forgetting his last name. Grant Sanderson, actually, not that bad. Who, in the meantime, he was initially, so most of these videos, like especially divergence, are from Grant. He goes by 3 blue, 1 brown. So the best mathematical concepts you can I mean, you kind of, you find yourself reading videos. Calculus, but they're good. It's one of those categories, like I wish somebody was using these when teaching me calculus back in the day, okay? That type of a thing. But not just calculus, there's all kinds of concepts connecting both math and physics. And it's definitely worth exploring those websites. They're not long videos. All of these are about 6 minutes. We're going to look at one of these divergence situation today. Anyway, but before that, I'm getting ahead of myself. What I wanted to review is what we went over last time, and that is basically generalization of the viscous stress tensor. So we know our parallel plates model. That is our favorite way to look and define viscosity. And this is a simple way where, this is a simple case where my velocity, I have only one coordinate direction velocity that is non-zero, the rest are zero. So I have this plate moving and pulling the fluid in x direction. And because of that motion, if I keep exerting force on that plate, okay, because of that motion, I'm going to start moving the fluid as well. And what happens is that fluid close to the plate, or fluid layers, the way we typically visualize those, they have larger momentum in x direction. And through molecular collisions, they start transferring that momentum upwards all the way up to the top plate that is sitting static. Over time, I will have this steady state velocity field develop. And by steady state, I mean it's not changing in time. Okay. So we really have these velocities that are just a function of position. And basically, when I look at this momentum transfer, stress per area, that lower portions of the fluid exert on the upper portions. Of course, the upper portions exert negative thing on the lower portions, mathematically, but just in this visual where I know that my velocities below are larger. This stress per area is a shear stress. It's in x direction across y plane. So this tau yx, it's proportional to dvx dy. And minus dvx dy is what we refer to as shear stress strain rate, gamma dot. And there's a coefficient of proportionality u that is equal to viscosity. Now I'm wondering, what does this like in a more general situation? Or rather, I'm forcing you to learn what does it look like, whether you're wondering or not. It's a good question. So in most general case, I have a velocity that has x, y, z direction. So across any plane that I put in my fluid, I can feel, if I have differences in velocity, I can feel the momentum transfer of all of these x, y, z momentum. Okay? So momentum is a vector, and its x, y, z components can transfer across three different planes. Okay? So now instead of just tau yx, so I used to have only x momentum, right? And my y and z velocities were zero, so nothing was transferring. So now I might have also y velocity or y momentum transferring across y plane, and z momentum transferring across y plane. So the vector that describes all of that has three components. It's my tau y, and basically I'm describing how x, y, z momentum that fluid has transfers across y plane. So that's what I mean. Across y plane is either some coordinate system. So I'm going from lower y coordinates to higher or upper or larger y coordinates across y plane. So that is my tau y. I can strike two other planes and have x, y, z momentum transfer across x plane. One of the x planes is one of these sides, right? So on x plane, x is constant. X is pointing in this direction. And for z plane, those are the bottom and top z planes. I can also have x, y, z momentum transfer. And I describe that with vector tau z. So I can put all three of these in a tensor, okay, or a matrix. And so I'll have, when I line them up, sorry, this is basically repeating. And I also have, in addition, the pressure acting. Pressure is always acting in normal direction. So technically, we don't need a vector describing it. If I put it as a vector, then my vector, for instance, squeezing things in z direction is 0, 0, p. Yes? 0, 0, p from this side, and minus 0, 0, p from this side. Yes? So this is basically what's it's a sort of a compressive action, and we take that, basically that's my 0, 0, p right here. Okay? So I can put that in a tensor as well. So when I add the two, I will get what we call total molecular stress tensor. P plus tau xx, tau xy, tau xz, tau yx, p plus tau yy, tau yz, tau zx, tau zy, p plus tau zz. Okay? And this is also identity matrix, p times identity matrix. So that's what I mean by basically pressure, just need one scalar to define it. And for shear stress, we need the full matrix. Now, let's just go back to definition, or how do we take what is positive and what is negative. It's opposite of what is going on in solid mechanics. There's a difference in convention in fluid mechanics and solid mechanics, but it's just that, it's convention. So basically, I'm going to take my tau yx, pointing at least nominally. Of course, if tau yx is negative, then it's in the opposite direction, actually acting in the opposite direction. But nominally, what I put tau yx as a positive is when I have sort of my fluid acting across this imaginary plane. So if I'm thinking like this is some sort of imaginary object sitting on the fluid, then here fluid is in a lesser lesser coordinates. Okay? And in this case, lesser y coordinates. And then I'm going to have it point in the positive x direction. Whereas when I look at the top of the plane, my imaginary fluid is sitting in larger y coordinates compared to the object it's acting on. And this is technically going to have the same value, this tau yx, just in the opposite direction. Okay? So direction, it doesn't matter where do I sit in the coordinate system. Okay? So whether this action or momentum transfer is in the positive y direction, the actual momentum transfer acting on this imaginary solid surface, then my tau yx will point in the positive direction set. And up there, I'm actually, my momentum transfer from the fluid on this imaginary solid object is in the opposite y direction, right? This is opposite the y axis. So that's what I mean that my fluid technically sits in larger y coordinates. And that's why my tau yx on this side, on this plane, shows. And then I have the similar story going on for tau xy. So this is transfer across x plane. Here, I'm transferring from lesser x coordinates to higher x coordinates. This is my x direction, right? So this is going to point upwards at tau xy, but it's the transfer of y momentum across x plane. Yes? Also, the force that overall this fluid sitting here is exerting on, in this case, my imaginary solid object sitting here. But I could also have fluid, of course. And then here, I'm acting in the direction opposite of the x-plane, or of the x-coordinate vector. So that's why my tau xy is pointing downwards. Yes? Questions? Let's see if that sits really well. So so take that piece of paper that I gave to you. And on that piece of paper, I want you to draw on this bottom plane. That's a Z plane, right? So on this bottom plane, draw the direction of tau zz, tau zx, and tau xy. Do you have a piece of paper? I think you can do it on your own. But this is just your. So tau zz, tau zx, and tau zy. On the bottom plane. So this would be the direction of tau zz. imaginary fluid is sitting in lower z coordinates, acting on some larger z coordinates. Basically, I'm going across the z plane in the z coordinate direction, right? Therefore, I'm going to point my tau zx in the direction of x or the other way. In the direction of x, right? And that's, again, a matter of if I have differences in velocities, vx velocities, and therefore differences in momentum below this z plane versus above, I'm going to have momentum transfer across z plane, but it's shear because my x velocity is shearing the plane, right? So in itself, that force per area that the fluid below exerts has x coordinate direction. Yes? Because of the x coordinate velocities. And then where is my tau yz point, zy pointing? Y momentum transfer across the z plane. It's y momentum, y velocity, so I'm exerting, or I'm looking at the portion that is exerting y direction force on the fluid above. There are questions about this. Again, it takes a little bit of, and kind of, you have to find a way for you to memorize these things.
You know how you're talking about the convention last time? I thought that tau z y would be the opposite. Like,
that's, so right now, I'm pointing it in this direction. Because again, I'm my imaginary fluid on this plane. I'm going from lesser y to upper y. In solid mechanics, it's going to point in the opposite direction. Okay, and that's again, those are two different conventions, but it's just that it's a matter of convention. But once you stick with one convention, you kind of have to be consistent. So this is my tau z. So it describes momentum transfer across the plane, and overall, it has some general direction that has x, y, z coordinates. Now, how would things look like on this? So this, which plane is this? So this is z plane. Let me change color here. This z plane, which one is it? No. I want to change color. There we go. So what is this plane? X plane. So what I would call upper X plane or higher X plane in this box anyway. Now my imaginary fluid sits in the larger X values, right? So the way I sketch these viscous stresses, they will point against the coordinate system, right? So there will be tau xx, right? What is this one? So it's against as a z direction or coordinate z direction, and tau so again, this describes momentum transfer across z-plane, and my tau x, tau xx, tau xy, tau xz. This is, of course, xy. It's very easy to flip things. That describes momentum transfer across x-plane. Now these are, and of course we would have tau z, tau y, if you just want for fun. Pick yourself a y plane and draw these. So these are viscous stress components. And the x, y, y, z, z, those are the normal stress components because they act normal on those planes, coordinate planes. xz, xy, zx, zy, and so forth, all of the others are shear components because they're acting parallel to the plane of transfer. There's pressure in all of this. Right, so it's in normal direction. So pressure always, so I'm imagining these planes, these little coordinate planes, and pressure always acts on any plane just in normal direction. There's no such thing as shear pressure, okay? If it's shear, it's some different type of stress. It's not hydrostatic pressure. This is pressure. On all sides, right? And from the back as well. So always normal to any surface. Yes? So please sign these. This will act as your today's quiz. So you get a quiz grade. It's really more like a attendance grade. Right? But we'll practice these because it's really just like it takes a little to memorize. So again, this is the summary of the what we call molecular stress components. So we put them in a table. P is added on to the normal components. Right? So when I look at them in this matrix mode, when I look at the first row, this is my tau x, 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 y, x, z, and added pressure in normal direction. So those are my total molecular stresses acting across x plane. Okay? And I have x, y, z components of the viscous stress tensor as well as the hydrostatic pressure. And when I look at one column, okay, those are just x, so x, y, z plane, or just x component of x, y, z. Yes? Okay. So before I now define, so all of this is building up. So now I have put them in a table. Now I have to figure out, well, what are those? We had tau yx in that expressed in that simple case of parallel plates. But I had only x component of velocity that was non-zero. And we had an expression for tau yx for all kinds of fluids. For Newtonian, it was minus mu dvx dy, correct? But my dx velocity, my velocity only Vx was non-zero, and it depended on y. So Vx was a Vx of y. So it's as simple as it could be. What if that V has all kinds of components, Vx, Vy, Vz, and all of them can depend on x, y, z? Well, in time, but we're right now looking at the steady state. Okay, so I need to actually review what is a gradient of a scalar function. This I mean scalar function. What is a gradient of a vector function, for which I need Jacobian matrix? And what is the divergence of a vector? All of those I will actually combine to define stress. So I'm going to actually play, so gradient, we know, so if I have a scalar function, and let's say that pressure is a scalar function, right? What is gradient of pressure? I often denote it as nabla P. Sometimes we will see also grad P. We will stick to this nabla P, partly because it's shorter and because book uses it, and there's another reason that I'm not going to go into now. But that's basically just a combination of partial derivatives. There does the gradient point to. When I have a general scalar field, I have pressure in this room. And at every point, I can have gradient P, dp dx, dp dy, dp z. So now this is a vector field. This gradient is a vector field. Correct? So at every point, I have a little vector pointing. Which direction is it pointing in? In general, like what is it telling? What is this direction? Let's say that the gradient of pressure is pointing in this direction. What is in that direction as opposed to this? Nobody watched the video. It's the largest change in pressure. So we have in that direction of a gradient. Gradient physically points in the direction of the largest change. Also sometimes called steepest ascent. If you're out there hiking and you get a contour map, and the contour map is showing you height function over an area. So that's the height of xy. And it's showing constant values of height, right? And anybody went hiking recently? No. Sorry about that. But you should. And before May 1st, then it becomes too hot. so take this time of the year in Texas and go some hiking. So then you have those contours where it's a constant value. And in some places, they're kind of bunch up. And in some places, they're kind of spread out. Which direction are you going to hike if you want a leisurely hike? Huh? Along one contour, because the hike is not changing. Where they're bunched up, across that direction is your steepest ascent or descent, depending on which direction you're rolling. That's basically that gradient direction. That's where gradient is pointing. On that contour where I have constant values, I will look, like at every point I can take a gradient or evaluate the gradient, and it's going to point in the steepest. And where contours are really spread out, that's also leisurely up and down. Okay? So know that about being engineer, know that when you go hiking, then decide whether you want a very good workout or not, or easier workout. So that gradient will tell you that. So if I had a gradient of a vector function, so now if I put a vector function, I'm going to write it in 2D. So let's say that my vector function v of xy has a vx component as well as vy component. What is my gradient of v? Is it how many values do I need to? So normally I know what is the gradient of a scalar function. Each of these is a scalar. So I can technically take a gradient of Vx and gradient of Vy. In 2D, how many components do I have for gradient of Vx? So I can take derivative in x and derivative in y. 2. 2 for this, 2 for this, 4. What am I going to do with 4? How am I going to put them together? Into a matrix table. So that matrix is Jacobian matrix. Does that ring a bell? Okay. What are we going to put in the first column? Essentially, first column will be my gradient of Vx, my scalar function Vx. Yes? And in the second column, the same for Vy. Another way to look at that is that in my first row, I have derivatives with respect to x of Vx and Vy. And in my second row, I have derivatives with respect to y of both Vx and Vy. The way we assemble these matrices is I take coordinate function by coordinate function for my vector field and do the gradient on them and just stack them together. Just think about that. So your first column is your gradient of Vx and the other one is gradient of Vy, if you ever need to remember. Now I'm not going to write divergence in 2D because it's actually written here. We use either nabla dot or sometimes we also use divergence of V. That's actually taking x derivative of Vx and y derivative of Vy and pulling them together. Is this a vector value or a scalar value? So divergence of a vector is a scalar value. And it's basically measuring how much for this field, how much of a sink or source I have. So around the point where it's evaluated, so this is my xy where it's evaluated, if it's positive, it appears as if overall this point is acting as a source. Like for instance, fluid is flowing out. Wellbore can be a source. During water flooding, however, during production, wellbore is a sink. And source and sink are actually terms used in fluid mechanics. So this flow field, and it could be flow field, it could be velocity field, it could be any other field. My divergence is kind of looking as a mass. Is mass kind of flowing up? Either flowing. If I do rho v, then my mass is flowing out, and here it's flowing in. And that's important in mass conservation. It's very important. Knowing where I have sources and sinks is very important in any kind of conservation law. And we love conserving mass, energy, and so forth in any kind of fluid modeling. Transport modeling, for that sense. Yes? I'm actually gonna play this intuition movie, if it plays.
All right, everyone. We've gotten to one of my all-time favorite multivariable calculus topics, divergence. And in the next few videos, I'm going to describe what it is mathematically and how you compute it and all of that. But here, I just want to give a very visual understanding of what it is that it's trying to represent. Divergence. So, I've got in the next few videos, I'm going to describe what it is mathematically and how you compute it and all of that. Understand vector fields. But here, I just want to give a very visual understanding of what it is that it's trying to represent. Every single point in space, I've got it here as pictured in front of us, like a vector field. And I've said before that a pretty neat way to understand vector fields is to think of them as representing a fluid flow. And what I mean by that is you can think of every single point in space as a particle, maybe like an air particle or a water particle, something to that effect. And since what a vector field does is it associates each point in space with some kind of vector. And remember, I mean, whenever we represent vector fields, we only show a small subset of all of those vectors. But in principle, you should be thinking of every one of those infinitely many points in space being associated with one of these vectors. And the fact that they're kind of smoothly changing as you traverse across space means that showing this very small, finite subsample of those infinitely many vectors still gives a pretty good feel for what's going on. So if we have these fluid particles and you have a vector assigned to each one, kind of a natural thought you might have is to say, what would happen if you let things progress over time, where at any given instant, the velocity of one of these particles is given by that vector connected to it. And as it moves, it'll be touching a different vector, so its velocity might turn, it might go in a different direction. And for each one, it'll kind of traverse some path as determined by the vectors that it's touching as it goes. And when you think of all of them doing this at once, it'll feel like a certain fluid flow. And for this, you don't actually have to imagine. I went ahead and put together an animation for you. So we'll put some water molecules, or dots, to represent a small sample of the water molecules throughout space here. And then I'm just going to let it play where each one moves along the vector that it's closest to. And I'll just let it play forward here, where each one is flowing along the vector that's touching the point where it is in that moment. So, for example, if we were to, go back and maybe focus our attention on just one vector, like this guy, one particle, excuse me, he's attached to this vector, so he'll be moving in that direction, but just for an instant, because after he moves a little, he'll be attached to a different vector. So if you kind of let it play and follow that particular dot, after a little bit, you'll find him, elsewhere. I think this is the one, right? And now he's going to be moving along this vector, or whatever one is really attached to him. And thinking about all of the particles all at once doing this gives a good sort of global view of the vector field. And if you're studying math, you might start to ask some natural questions about the nature of that fluid flow. Like, for example, you might wonder, if you were to just look in a certain region and count the number of water molecules that are inside that region, does that count of yours change as you play this animation, as you let this flow over time? And in this particular example, you can look and it doesn't look like the count changes, certainly not by much. It's not increasing over time or decreasing over time. And in a little bit, if I gave you the function that determines this vector field, you will be able to tell me why it's the case that the number of molecules in that region doesn't tend to change. But if you were to look at another example, like a guy that looks like this, and if I were to say, I want you to focus on what happens around the origin, in that little region around the origin, you can probably predict how, once I start playing it, once I put some water molecules in there and let them flow along the vectors that they flow along, the density inside that region around the origin decreases. So we put a whole bunch of vectors there, and I'll just play it for a quick instant, just kind of let it jump for an instant. And one thing that characterizes this field around the origin is that decrease in density. And what you might say, if you want it to be suggestive of the operation that I'm leading to here, is that the water molecules tend to diverge away from the origin. So the kind of divergence of the vector field near that origin is positive. And you'll see what I mean mathematically by that in the next couple of videos. But if we were to flip all of these vectors, right, and we were to flip them around, now, if I were to ask about the density in that same region around the origin, you can probably see how it's going to increase. And when I play that fluid flow over just a short spurt of time, the density in that region increases. So these don't diverge away, they converge towards the origin. And that fact actually has some mathematical significance for the function representing this vector field around that point. And even if the vector field doesn't represent fluid flow, if it represents like a magnetic field or an electric field or things like that, there's a certain meaning to this idea of diverging away from a point or converging to a point. And another way that people sometimes think about this, if you look at that same kind of outward flowing vector field, is rather than thinking of a decrease in density, imagining that the fluid would have to constantly be repopulated around that point. So you're really thinking of the origin as a source of fluid. And if I had animated this better, a whole bunch of other points should be sources of fluid so that the density doesn't decrease everywhere. But the idea is that points of positive divergence, where things are diverging away, would have to have a source of that fluid in order to kind of keep things sustaining. And conversely, if you were to look at that kind of inward flow, or what you might call negative divergence example, and you were to play it, but it were to go continuously, you'd have to think of that center point as a sink, where all the fluid kind of just sort of flows away. And that's actually a technical term. People will say the vector field has a sink at such and such point, or the, electromagnetic.
Yeah, so you essentially get the idea. So sources and sinks. Therefore, I'm a source. Or for the producing, when you're producing, you're a sink, hopefully.
Magnetic field has a sink. It's multivariable calculus topics. Divergence. And in the next few videos, I'm going to describe what it is mathematically and how you compute it and all of that.
And what I love about the videos that follow, they actually kind of intuitively explain why to describe divergence the way that you have to actually have divergence. So I think that helps them use the formula. Ultimately, gradient divergence is used in the formula. Just memorize the formulas or look them up and use them. Okay, no problem. But it's actually really nice to understand why is it so, especially if the form. So what I expressed here is on the, oops. What I expressed here are formulas that are tied to the Cartesian coordinate system. These formulas will change in a different coordinate system. And it's actually useful to then have a physical view to understand why. So we will get to that point right now. There's no, we will not gain any more understanding if I introduce other coordinate systems. All right. So now what is my generalized Newton law? Tau ij, and ij could be either of the x and y. So let's assume this is tau yx. Then instead of I will write a y. Instead of j, I will write an x. It's minus mu dy dx plus dv dx dy. So I don't only have just one anymore. We used to have tau yx is, write that. So we used to have tau yx is minus mu dx dy. But that was for the case of v having vx of y and no other components. Now if my v actually does have other components, so I have v in general as vx of xyz, vy of xyz, and vz of xyz, and it's very characteristical of me to run out of space. A coefficient here. We're going to explain the coefficient. That coefficient uses both viscosity and another one called the rotational viscosity. dvx dx plus dvy dy plus dvz dz. Delta xy. And this delta xy is so-called Kronecker delta. And if I is different from j and x is different from y, it's going to be 0. So what I'm going to have in general for tau y It's minus mu d by dx plus dx dy. And this one will be 0 because my Kronecker delta is 0. This here is divergence. So this is, well, I actually probably have, this is divergence of a vector field. And in tensor, so this is a shorthand notation. d by x, d by v, dx plus ddx dy. It's basically like adding a yx component of gradient of v, which is my Jacobian matrix, plus the transpose of it, the symmetric transpose. So this is my tensor tau. This is the shorthand notation for the tensor. And this is identity matrix. It really has ones on diagonal and zeros otherwise because this Kronecker delta is 0. So this is an identity matrix. So this is my tensor. This is just a scalar divergence. And it's just a measure of whether I have a source or a sink in a point. For incompressible fluids of constant density, this is a 0. So most of the time you're not going to have this. Okay? So this is for incompressible fluids. Most often, if density constant, then my incompressibility is basically divergence is 0. So I don't have a source or a sink. And this T is the matrix transpose. So this is just a shorthand notation. This one is easier to apply immediately. So on your little slip of paper, can you write down what is tau xx? So, do you have a slip of paper? Because this is going to be a quiz for today. So if not, take a piece of paper. Oh, you have an extra? Okay. It's going to be 2 of them, yes? dvx dx plus dvx dx is 2 dvx dx. It does not sort of correctly generalize. Don't forget the 2 when you have xx, right? For tau x. Remember to look these up. Look these up. Your homework that will be today, we will give you velocity field and practice finding shear stresses of all kinds. So it's going to feel like calculus exercise, but it does have, since these shear stresses are, you can calculate total force on on a solid that is neighboring fluid, it's an important physical implication. Just one more thing. As we viewed that volume of dots in the video, you had constantly fluid particles moving through it. So for a fixed control volume of anything, okay, there is constantly different, my volume is constantly seeing different molecules of fluid. So some of the momentum is simply moving in. Okay? So we call that convective momentum. And if we monitor what's actually moving in, for instance, across y plane, there is momentum rho v across y plane moving vx. So rho v is the momentum times vx is basically momentum carried in across y plane. So that momentum has then three components: vx, vy, vy, vy. So this is my rho v multiplied by vy. And you've guessed it, I will assemble these into a matrix and add them to everybody. So this is my convective momentum that is carried into volume with different fluid particles. So now we have molecular and convective. Yes? All right. I see you on Wednesday. Sorry to go a little overboard, but nobody watched the video, so I had to replay it.